Hi everyone, welcome to the Structural Dynamic lecture series. In this present lecture, we will be talking about the response of a damped single degree freedom system under force vibration, also called harmonic vibration. Now, if we look at the equation of motion for force damped force vibration, which is mx double dot plus cx dot plus kx equal to f of t, which is f of t is f naught sin omega bar t. That means f naught is a maximum force and is varying like a sine, and f omega bar is a forcing frequency. So now this then differential equation is non-homogeneous, and if you look at the system, this is a damped system, single degree freedom system, subjected to the exerting force, which is harmonic force. Then this particular frequency is a forcing frequency or a operating frequency. If you look at the system of forcing frequency, it varies like a sine, and maximum amplitude is your f naught. Now again, because it is non-homogeneous differential equation, it has got two different parts of solution, and dividing the equation into two parts, when it's particular part and homogeneous part. Particular part gives steady state response, homogeneous part gives transient response. When combine them, we'll get a total response. So the assumed response is g1 sin omega bar t plus g2 cos omega bar t, and g1 g2 are the constants. It is to be found out by substituting this equation response into the differential equation. So taking first derivative of the response, then differentiating of this, then doing one more differentiation, second derivative of the response, and obtaining this response, and substituting into the particular solution, equation of motion, then comparing the LHS and RHS, the sin omega bar t and cos omega bar t coefficients in the left hand side. So what we get is this, and taking g1 in the common, then comparing the cos terms, this cos omega t is not there, so that's 0. So these two equations obtained by comparing LHS and RHS of coefficient of sin omega bar t and cos omega bar t. Then taking g1 common in the first equation, taking g2 in the common in second equation, then we get from the first, I get k minus m omega bar square g1 minus c omega bar g2 is f naught. In the second, I get, sorry, this must be, there must be g1, this must be g1, k minus omega m omega square g2 minus c omega bar g1. So solving these two equations 3 and 4 for g1 g2, so for solving, before that, what we can do, divide this equation 3 and 4 by k, and once you divide by k, and we need to do certain assumption here, the beta is omega bar by omega, and the c to be written as 2m omega xi, and k is m omega square. Taking these known things into this equation, so we'll get this form. K by k become 1, m by k will be 1 by omega square, omega bar square by omega square is beta square. So that's how I got 1 minus beta square g1 minus 2 xi beta, because c is nothing but my 2m omega xi. Okay. So then m by k is omega square. So omega bar omega cancel, then omega bar by omega becomes beta. So this way I get this, and the next second equation I get 1 minus beta square into G2 minus 2 xi beta G1 equal to 0. Now solving for G1, G2. Instead of this stage, I can solve the second stage. It becomes easier. So now by solving that find 6, I get G1 and then I get G2. Then plugging in this G1, G2 into the response xp of t, I got G1 sin omega bar t plus G2 cos omega bar t. And since I have some common terms, taking the common, so f naught by k, which is nothing but we know xst by 1 minus beta square whole square plus 2 xi beta whole square, and this. Now it looks like something into sine minus something into cos. So total response can be put into either sine or cos, sine omega bar t minus something. So single sine term. So sine A cos B minus cos A sin B, sine of A minus B. So putting in that form, so we can get this. This means is a cos term, right? So but this is 1 minus adjacent, and we say angle is psi, and this term will be a sine because we want for sine. So this hypotenuse, that means 1 minus beta square by this hypotenuse becomes cos psi, and this by hypotenuse becomes sine psi. That way sine of A minus B can be written. So that then tan psi will become 2 xi beta by 1 minus beta square. This psi is called phase lag, the phase angle between the response and the applied force, and this psi is always between 0 to 180. So by rearranging this term, so what we get, sine of omega bar t minus psi. So this remains. Okay, because here I need to divide by the hypotenuse and also multiply, then these two together becomes a denominator under root. So now this becomes a transient response, steady state response. Then looking for the total response, x of t, xp, particular solution, and harmonic, steady state and transient response. Now I got a steady state response. To get the transient response, I need to give initial conditions to get the amplitude and phase angle. So but we know that this is not very much important when it comes to the damped force vibration, but anyway, so we can use the initial conditions. It will die down after some time, therefore it can be neglected. So the final response will be a steady state response having only the first term, which is xst by 1 minus beta square whole square plus 2 xi beta whole square under root into sine of omega bar t minus psi. So if you look at here xst, when this x of t, which is dynamic response, will be maximum when sine term becomes 1. When sine term becomes 1, this will be maximum. And then this x of t max by xst, then this will be 1. Then that the right hand side will become 1 by under root of 1 minus beta square whole square plus xi beta square. This is called dynamic amplification factor or dynamic magnification factor, also is also DAF. This is what very important for the design. Okay. Now if you look at the response of the system, what we have x of t, and see this is the total response, and this red one is steady state response. Within half a cycle we have a response is the total response is nothing but a steady state response. That is why we have neglected the transient response. So this, what is the transient? This response is going along the steady state, little transient here. But finally, only steady state response only governing. So that's why we can neglect the transient part. So now if you look at carefully what is the dynamic amplification factor and how it is affected by the damping and the frequency ratio. So if you look at this dynamic amplification factor, x of t max by xst is 1 by 1 beta square whole square plus 2 beta whole square. Now how this is changing with the frequency ratio? Of course, because there is another variable called xi, we need to take a particular value of xi and understand the variation of beta. So what we can draw a curve for different damping ratios. If a damping ratio is 0, this is the first blue one, at a particularly the beta, the frequency ratio of 1, we have an infinite solution. That means this solution becomes impossible, because beta equal to 1 and beta equal to 1, this is 0. When xi equal to 0, this is 0. So 1 by 0 is infinite. So at 1, infinite. Okay. And as xi increases, see at beta 1, although there is a resonance, but your amplitudes are reducing. So it's not a dangerous thing. So what we can observe, the displacement decreases with increase in damping. That's what we observe. As damping increases, this is 10%, 20%, 70%. As damping increases, the displacement gets reduced. And if you look at for beta equal to 1, that means at this point, the displacement amplitude is maximum. See here, a maximum, this is maximum. So at 1, displacement is maximum. That maximum is, if you look at this response, substitute beta equal to 1, so this term is 0, the square and square root get cancelled, so beta is 1, so 1 by 2 xi. So dynamic amplification factor is 1 by 2 xi. Now for near beta near to 1, not exactly 1, near 1, that means somewhere around here, somewhere around here, right? At this zone, see what happens. The factor is very sensitive to damping. If this is this side lesser than, the moment you have damping less, damping increases, suddenly reduces. So damping is a lot of influencing at near to that beta, near to beta. Now for beta less than, very much less than 1, that means this zone, that means somewhere here. Very much less means less than 0.5. So dynamic amplification factor slightly more than 1. See here, at this point, slightly more than 1 here, except this first one. So the is more than 1. And it appears to be independent of damping. Almost all curves here and the zone are the same point. So damping does not make much difference when beta is very much less than 1. But so what happens? That means your dynamic amplification factor is close to 1, or that means what? X max by xst is equal. These are equal to 1. That means maximum amplitude is equal to xst. That is f0 by k. K means m omega square. That is how we can say it is independent of damping. Now, suppose beta is very much less than 1. That means around this, from here, more than 2, let us say. What happens? The dynamic amplification factor tends to 0. And essentially there also is independent of damping, because all curves are meeting the same point. So either your system has a damping or not having damping, no meaning. So no need to struggle hard to induce damping when you are working with a frequency ratio more than 2. If frequency ratio more than 2, you don't have to worry to induce damping in the system. Okay, so now that means dynamic amplification factor, which is very close to 1 by beta square. 1 by beta square. More than that, because this, when ratio is very high compared, so this 1 is negligible compared to beta square term, right? So then this and this point, you can very well, xi is negligible because damping is not there at that point. We don't worry about damping. So 1 by beta square. So this square root can cancel. Only beta square term is remaining in the system. So that means x max equal to xst by beta square. Beta square means xst means f naught by k. Beta square means omega r by omega. So then we can get f naught by m omega square. So this is the learning lessons from this dynamic amplification factors study. Now there is something called phase lag as phase angle. That is tan psi is to xi beta by 1 minus beta square. If you try to plot with the different betas frequency ratio, but again since I have another variable xi, so various xi. So this is xi equal to 0, which is exactly the vertical. And as the xi increases, damping ratio increases, so curves towards the left. Less than beta less than 1 curves on this side, and beta more than 1 is curved on the right hand side. So what observation we can make, when frequency ratio is very much less than 1, that means somewhere around this zone, somewhere here, less than 0.5. So what we can observe, the phase angle is close to 0. Phase angle is here is close to 0. Then the displacement is in phase with the force. That means whenever the force is this side, displacement is this side. When force is this side, displacement this side. So that means that the force is in phase, or displacement is in phase with the force. Okay. Now, when frequency ratio is very much more than 1, that means somewhere here, this is zone, very much more than 1. What happens? The phase angle close to 180. So we will get here, as it goes on increasing, so you will see somewhere this all slowly goes to like this to 180. So close to 180. That means the displacement is out of phase with the force. When force is this side, displacement is this side. When force is this side, displacement this side. So they are out of phase. This is out of phase. That is why with high frequency, it doesn't look like this structure is vibrating, because force goes, the displacement this side. So almost like structure is steady. Force and displacements are opposite in directions. The frequency ratio equal to 1, then what happens? The phase angle is equal to 90 degrees here. So when frequency ratio is 1, his phase angle is 90 degrees. That means displacement is out of phase with the force. Okay. So that means the displacement attains peak when force passes through 0. That means whenever we have the force responses like this, when it passes through 0 force, this is f of t. When force passes through 0, here, these points, your displacement becomes very high. That is when frequency ratio is equal to 1. Thank you.